Hello to everyone and welcome to today's webinar. My name is Jeff Duck. I'll be the presenter from Cascadia Windows and Doors today. We will be talking about navigating building energy performance standards. And we are right at 12 o'clock and I see a few more people joining right now. So I will just give everyone at least one more minute to get online. And if you need to refresh your coffee or get your lunch, please go ahead and do so now. We can also cover a few housekeeping items while we're waiting for the last few people to join today. So if you need any technical support on today's webinar, please refer to the GoToWebinar support information that was available in your registration confirmation. Please contact them and hopefully they can sort out your issues quickly. If you have given us your accreditation for continuing education credits, we will submit on your behalf at the conclusion of this webinar. So no need for you to do anything if you've supplied that information. Thank you for that. If you require the confirmation of attendance or anything to self-submit, please do contact us after the webinar. You will receive confirmation that you attended but approximately 1 to 2 hours after the conclusion of today's webinar. But if you don't receive anything or if you need another copy, feel free to just reach out to us and we can send you your confirmation. Questions, please do ask questions during the presentation if you'd like to. There is a question and answer function to the GoToWebinar software. Please put your question in that and I will attempt to answer anything as we go here, and then if not, we will have some time at the end for a question and answer as well, or I can follow up after the webinar as well and answer anything that might be project specific. Finally, audio, we recommend that you use a computer, your computer audio to listen to the presentation. There is dial-in option available, but can be expensive with long distance, so GoToWebinar audio through the computer is the best option. I see we have one comment in the question and answer box, so it looks like it's working. So that's great. I'm going to go off camera and we're going to just maximize bandwidth and viewing screen for everyone. And I'll come back on at the end of the presentation for the question and answer period. And so without further delay, let's get into today's agenda. So here's what we're looking at. We'll do a brief intro into Cascadia Windows and Doors. Who are we? And then why are new building energy performance standards, or BEPS as we'll refer to them for short, being introduced? How do current BEPS differ from previous performance metrics? We'll explore design flexibility offered under these new building energy performance standards. And we'll also do an introduction into high performance fenestration options. And finally, cost optimization. How do you cost optimize those high performance options so that we're not spending more than we need to on making our buildings comply with these new energy standards? So an intro into Cascadia Windows and Doors. Who are we? We manufacture fiberglass building envelope components, specifically windows and doors for commercial and multifamily projects, as well as for residential projects, passive house, high-end residential, step 4, step 5 energy code level residential projects that obviously have targets that they're trying to meet and codes that they're trying to comply with. We also manufacture a fiberglass thermally broken cladding attachment system called the Cascadia clip, and you can see the picture there on the right. So this Cascadia clip is made from fiberglass and thermally breaks the cladding attachment from the substrate that it's attached to and prevents heat loss through that cladding attachment. So in conjunction with our windows, fiberglass frames, and Cascadia fiberglass clips, a very efficient material for energy efficiency on the building envelope. If you're interested in some of our other window products, we do have webinars that are specifically dedicated to those product types. One of them being North America's first window wall for multifamily, so slab to slab window wall. That there's a webinar on that I would encourage you all to attend. Also, our punched and strip windows, commonly found in that passive house residential type project. And then also we do have commercial storefront glazing options. So factory built with the performance levels that you have come to expect from fiberglass windows and doors and commercial windows. So that's our product portfolio. Our company is located in Langley, British Columbia, which is a suburb of Vancouver. Started in 2008. Primary markets for windows and doors have been the West Coast of North America, basically. However, we are seeing some more and more opportunities and jobs that are using our products in New York, Boston, DC, Philadelphia, areas where codes are just becoming more and more stringent and people are looking for solutions there. And that ties into our company's purpose, which is to provide simple and cost-effective solutions to more stringent energy code requirements. And we're seeing those stringent energy code requirements all over North America and all over the world for that matter. So why is the question, and the problem with buildings is an answer. The world's changing quickly. This is obviously a graph of historical carbon levels in the atmosphere. And you can see that in the relatively recent past, there's big change and we're seeing higher levels than ever before. And the challenge is that buildings are responsible for a large part of those carbon emissions, CO2 emissions, about 44.5% in the US, and the statistic is similar in Canada. So buildings are contributing a lot of CO2 to the atmosphere, and we as an industry have the opportunity to build better buildings that reduce the amount of carbon, reduce our footprint there, and can make a big impact. You can see as a group, buildings are much bigger than industry and or transportation when you consider that as a whole. So not only passenger vehicles, but also trucking and air freight and sea shipping, et cetera, et cetera. So buildings are consuming a large amount of energy. And you might say, you know, Jeff, this is great, but why don't you focus on electric cars instead of better buildings? And, you know, while that's definitely a subject that needs attention as well, you can see that buildings are much larger than transportation, as I mentioned, and you know, electric cars for passenger vehicles is only one small portion of transportation. So by addressing buildings and then commercial and residential buildings being 19% and 22% respectively of that 41% makeup there of buildings, by addressing those, we're poised to make the biggest impact by making those buildings more energy efficient and using less energy consumed from non-renewable resources is a key. So a lot of areas still in North America are consuming a lot of non-renewable resources. So like coal and natural gas are generating that energy. So we're obviously wanting to minimize that and move away from that and improve on that if possible. So what I'm going to do now is look at the history of the performance of a couple of different buildings. I'm going to launch a poll here. So this is an interactive part of the presentation. And if you've been through this before or seen this before from Cascadia, thank you for attending previous, and you can still play along. But for those of you that haven't, I'm going to launch the poll, and you can basically select your answer when the poll gets launched. So what we're gonna attempt to answer here is the R value of each of these three buildings. I'm going to show three buildings, and we're going to make a couple of comments about what makes up the building enclosure, and then I want you to guess what is the total R value of the building's enclosure. So I'll circulate the poll onto the screen, and it'll be multiple choice. So this is the first building. This building is located in downtown Vancouver, British Columbia. It's over 80 years old, and it has a brick veneer over a steel frame wall with some installation in the framing. The windows on the building are all relatively small punched windows compared to today's standards. And there's also insulation on the small roof area that you can see there in green. So taking this all together, what do you guess is the R value of building number 1? And I'm going to launch the poll now, so you should be able to see that on your screen. Please go ahead and make the selection as to what do you think this building's R value is. And thank you very much. I can see that everyone's putting in their answers now. It's great to see that audience participation. Really appreciate that. We'll give a couple more seconds here for the last few people to enter their answers. And so now I'm going to close this poll and I'm going to share the results here. So most folks think that the building's R value is R2 to R3.5, but we had selections through the full range. So some in R1 to R2 and some R10 to R16, so all the way through. So we've got some optimists and some pessimists in the group here. So thanks again for that. We will hide that, go back to the presentation, and I'm going to show you building number 2. So building number 2 is over 35 years old. It's a concrete structure. It is exposed on the exterior. About 50% is concrete and has a steel framed wall inside of that steel frame is where the insulation is. And the windows are aluminum frames. So the aluminum windows that you're seeing there are not thermally broken. 35-year-old building. So considering those exterior assemblies, concrete, steel frame with insulation, and non-thermally broken aluminum windows, what is your guess on the R value for building number 2? So we'll launch that poll now. And thanks again to everybody entering their votes, their answers, I should say. Almost done here. A couple more seconds. Okay, and we'll share the results. So I may have biased things a little bit, but with my presentation on that one, but the majority of folks, again, in that R2 to R3.5, followed closely by R3.5 to R6. So a little better than the 1930s building, but nobody thinks it's an R10 to R16. So great, thank you very much for that. We'll move on to the third and final building. So this is a much more building with much more glass. This building's fenestration system is a double glazed, thermally broken aluminum framed window wall, which includes a slab bypass. That's the portion of the system that covers the structural slab. It has some insulation at that slab, but there are also exposed slabs that you can see on those balcony stacks. And so there are exposed concrete slabs as well. So given that, what are your guesses at the R value of building number 3? And I will launch that poll now. So please go ahead and enter your guess for building number 3. Very glazed building, double glazed, thermally broken aluminum frame window wall. Okay, looks good. A couple more seconds for those last few to enter their vote, their answer. And I will share the results here. So another good mix of answers throughout the spectrum, and the majority of people actually thinking R6 to R10, so a better performing building than the other two for the majority. So thank you again, and I'll go back to the presentation now and conclude that all the buildings actually have an R value somewhere between 2 to 3.5, which was the second out of the 5 guesses for each one of the polls. And so what we can observe from this is that actually, if you look from left to right, that's where the high end of the range starts. and then declines to the low end of the range as we get to the more modern building. So actually the building from the 1930s was closer to that 3.5, R3.5, and the modern building with all the glass, double glazed aluminum window wall is closer to R2. So I want to point out that we're not making a case here that our carbon emissions are related to a problem of old buildings versus new buildings. That's not a good way to characterize the problem. The other thing that we're not, as an industry, really doing is making buildings all that they can be from a thermally efficient perspective. So naturally, they lose a ton of energy when it's cold or gain a lot of unwanted energy in the hot summer. So again, this is not an old versus new building problem, it's a performance problem. So because of society's needs and because buildings are not historically performing very well, we're seeing more and more quickly, more comprehensively than ever before, provinces and cities all around North America and beyond, and the rest of the world as well, dictating better performance from their buildings. And this slide shows a number of jurisdictions that have recently put in more stringent energy codes than ever before. So thankfully, energy conservation in buildings is improving, and it's going slowly, but it is moving in the right direction. However, for regulatory changes to be based in reality, first the industry has to have the technology, and then the regulators can change the laws to require higher performance from that type of technology. You can't do it the other way around. It doesn't work. So we view this as new building technology actually enables the regulations to become more stringent over time for the eventual good of us all. So what we're going to do now is look more in depth at two examples. We're going to look at what's changing in two major cities in the Pacific Northwest, Seattle in Washington and Vancouver in British Columbia. So both an American and a Canadian example. And there's not really much that's predictably American or Canadian, but what this example actually serves to do is show minor differences in energy codes that actually have the same concepts and the same physics involved in the ease of compliance. And it's relevant for people who are even outside of these regions, so all across North America, because future energy codes or modifications to energy codes and improvements to existing codes will be based on the same targets and the same physics as in these two examples. So it will still be relevant. So we're going to look at Seattle's implementation of the 2018 Washington State Energy Code, and we're going to look at British Columbia's implementation of the BC Energy Step Code. So before we get into that, there are limits to the session today. We'll define the scope. You're not going to learn how to become an energy modeler in the next 30 minutes, I'm sorry to say, and I would not be the one to teach that, even if it were possible. Compliance with energy codes as a whole, especially for big buildings, is achieved through multiple energy efficiency measures. But we have to all start somewhere, and somewhere is implementing those measures. So what we'll explore here today is the most efficient starting point to end up with energy code compliance. So the codes are different. There's a key way in the way this version of the energy codes differs from all other energy related codes and building requirements for insulation or building envelope performance for building performance in general. Let me first characterize what was in the past, even in the recent past. So the recent past worked like a recipe, and the recipe dictated that assemblies have to meet certain levels of performance. U value for the walls, U value for the roof, U value for the windows. And so there was this list of targets that acted like a recipe, especially if you're pursuing a prescriptive path for compliance. And it would give you these separate targets for the roofs, as an example, and for the fenestration. And in fact, even though it was a disjointed approach, it became even worse when we realized that there's no requirement for how these components connect together and the performance of that connection. So this also fails to actually tell you what is the required result. It's almost as if you have 5 ingredients in front of you to bake a cake, but you don't know anything about baking a cake. So which ones do you mix together in which sequence, and when do you put it in the oven? And if you didn't know any of those things, you could probably figure it out through trial and error, but you wouldn't have a result that was worth much at all while you're going through that process. Now, compare that item by item approach in old energy codes to the new energy code, and specifically this example is based on the BC Energy Step Code. There's one energy use limit for the building, and the key thing here is per square foot of this building, per square foot of floor area, there's a limit to the amount of energy that may be consumed in a year. So that's it, that's what you get. You can use it any way you like, but that's your limit and you have to work with it. So it doesn't require a certain target for the windows or walls or even for the roof. It doesn't really matter except to the designer and the energy modeler that's getting the math right to start with. In the end, you just have to achieve that result any way you want as long as it works. And we've seen this whole building outcome-based target approach work already. And where we've seen that is under the brand name Passive House, whether that's Passive House Institute International or Passive House Institute US. That has been the way the Passive House guidelines have been targeted. It's a mathematical collection of equations that add up to, do you have a building that is modeled to operate within a limit of energy use per year per square foot, or does it exceed it? And it doesn't mandate prescriptive targets for each individual assembly, and it doesn't mandate limits to glazing area, and it doesn't mandate certain types of mechanical systems or anything like that. It's just meet the result. So the reason this made sense is because if you think back to older codes like ASHRAE, for example, with individual targets for the roof and the wall and the windows, and you said, okay, well, that doesn't really address thermal bridging that's happening between those assemblies. It would be impossible to develop enough prescriptive detail to account for every influential factor, like all the thermal bridging in a building, while at the same time having a standard that's simple enough to actually follow and achieve. It would just be overwhelmingly complex and confusing if it addressed enough factors in the recipe approach. So instead, this is all simplified if we just have to design for results as opposed to prescribing the inputs. So it creates a massive amount of flexibility from a design perspective, and at the same time imposes responsibility that whatever you do, it produces the result. So let's look specifically at the first of the two step codes, and that's the BC Energy step code. So what are steps? And Seattle's code actually has this too, they just don't call it steps. The steps in the BC Energy step code are levels of energy efficiency, which limit the amount of energy used per square foot per year, and they are increasingly a tighter and smaller limit. So from a base perspective, built to code building, at the year this step code was introduced, there was a reference house created as a base case, and then each individual step is an improvement on that reference house base. So now each step 1, step 2, even step 3, are reasonably easy to meet, especially if you understand the relationship between things in the building enclosure. That's really the key to meeting the steps. So for example, if you had a step 2 or a step 3 building, and you're very familiar with building a well-built to code house that you wanted to upgrade, the only real things you'd have to do is give better attention to your air barrier strategy and potentially use a slightly better window and door product. You might have to use a bit of exterior insulation on step 3, but there are other ways about going about that. It's definitely not a necessity, and so that's not too hard to meet. But the higher levels for residential homes, step 4 and step 5, or for larger scale buildings like commercial buildings, even step 3 and step 4, those are all a different animal. They're a bigger stretch. They require a more sophisticated whole building approach to achieve them. And as a result, that's typical these days. In the early part of the pathway from 2017, when this was published, up to 2032, when it is envisioned that the very basic building code compliance will be the top level of this step code, that between now and then, incentives will be the most logical way to encourage the construction community to learn and adopt these higher targets. So here's that pathway to 2032, where we're all net zero ready. So steps: incrementally tighter limits on energy use per square foot. The existence of a code that's formatted this way is valuable and a well-built regulation for users like builders and architects, because this creates continuity across regions. So one energy code for British Columbia, but at the same time, the way it's designed also creates local flexibility on a city by city level. The cities can choose any step that's at or above the basic building code of the day, which right now is between step 1 and step 3 or step 4, depending on where you are in the province. And they can choose that step, or they can choose a higher step, depending on what the regulators in the local area believe is appropriate for the construction community they're most familiar with. And they can offer incentives of their own design on higher steps. The only thing is that no city may modify the steps. No city may say, okay, we're going to build to step 3, but we're going to deduct this and add this. That's not permitted. So it creates this understandable level playing field that's consistent. And yes, the steps may differ from city to city, but what the steps are do not differ. So you can become familiar with them. And that's one of the reasons this is regarded as a well-designed regulation. There's also value in knowing future targets for the industry participants, for manufacturers, for builders, for architects. And this is way more important than people understand at first glance. It gives you the opportunity to skip steps. So why do you want to skip steps? In short, financial reasons. So for the builder, training tradesmen, product knowledge, and the cost associated with all of those things. For the architect, modifying details and redeveloping specifications. And for manufacturers, redesigning and improving products and factories that make those products. It costs a lot of money and time to retool or retrain processes and factories and people. So to just do it once or twice over this period of time, this 15-year march towards the top step, not 5 times every time you change a step, you can just pick a couple targets that make sense. And once you've got it, it may take a few years for the codes to get to your level, but you future-proof your organization or your product line or your building company by doing so. So to be clear, we're all going to be building to net zero ready construction in 12 years or less. And this will be a built to minimum code building. So as businesses, we all need to get used to the necessary technology and the methods that make it possible before it becomes the legal minimum and has increased risk. So now we'll look at what Seattle has done, and Seattle's done some admirable things as well. Seattle's current building code, the 2018 version of the Seattle Energy Code, it still has multiple compliance paths. It's not totally gone to the one single path, the way I described the BC Energy Step Code. It includes a prescriptive path as an option, and it includes a total building performance path as an option, which is essentially a trade-off path. But it has a newly introduced outcome-based energy budget compliance path, which is the one that is more similar to the BC Energy Step Code, and it's the most flexible physics-based version. So we're really glad to see that come into this building code, and we think that eventually it's going to be the prevailing method for compliance, even though it might take the industry a few years to adopt it as the majority choice. The code also contains the value of future targets. So for this code, 2018 is the now, and then there are 4 future increments out to 2030. So for Washington State and Seattle and any other state that would mimic a similar approach, the future targets are set out for the good of the industry participants, just like they are in the BC Energy Step Code. So let's look at the whole outcome-based approach. And first, we'll look at the total building performance approach because it's a trade-off path and it's along the same lines as the outcome-based approach, but it's more related to the way energy modeling has been done for years leading up till now. It uses math and area-weighted averages to compare your design to a prescriptively compliant building of the same building type. So in doing this math in Washington State, except for Seattle, your calculated building envelope the overall weighted U value average may be up to 20% worse than the prescriptive building that you've modeled. This is permitted. And one of the reasons why that is the prescriptive model that you've input your math for doesn't address thermal losses between assemblies. So you're going to account for some of that stuff, some more stuff in your model, and that's why it's allowed to be up. That's why it's allowed to be up to 20% worse. But in Seattle, you cannot use energy modeling to make your building envelope any worse than the prescriptive model. So there's no permission for more sophisticated math to have the allowance to make your building worse. No, you still have to make a good building. So why model at all? Why not, since there's a prescriptive path, just follow the recipe and keep consistent with what we've been doing for the longest time? Well, one of the many examples that relate to optimizing design and cost optimizing how to achieve it is increasing the glazing area of the building that you're going to design and build. Prescriptive limits are generally 30% glazing area in this current and upcoming code. There are some conditions that are approved up to 40% with improved windows and or daylighting, but generally speaking, 30%. So that's fine for libraries or grocery stores or buildings of those type, but not so much for selling desirable homes, residential condominiums, for example, or office spaces that are potentially targeting more than 30 or 40% glass. So energy modeling permits a variable glazing percentage. In the Seattle code, the modeling comparison between a prescriptive building for the building type has certain relaxations for certain fenestration types if you're going to choose to use them. And those fenestration types that have relaxations are curtain wall and storefront, which we know from earlier versions of building codes, and newly any AW class window. So this AW class is a physical test standard that relates to the North American Fenestration Standard, NAS. So AW is the highest out of 4 classes that relate to a product's strength and durability. So if an AW class window is used of any frame type, fiberglass, plastic, metal, whatever, your model's prescriptive building, the hypothetical compliant with the prescriptive path building, can use the relaxed fenestration U value that comes with this option. Although your actual building will use the actual U value of the product you're going to use, and thus increasing the beneficial difference between the U value in the base model and the U value in your actual building. So that increases the difference of that U value that fenestration brings to your calculation. And so bluntly stated, if you find and use some AW class high performance windows, your model becomes instantly very flexible, especially if you're trying to maximize the glazing area. And so here are the actual numbers. In the location of Washington State, outside of Seattle, the U value for windows is U.30, except that if the fenestration type is curtain wall, storefront, or AW class window, the U value is 0.38. So now if you have a product that is 0.25 and you're going to use that product, that's what's going into your math on your building. The U value that you're going to put into the prescriptive building to make a comparison is either U.3 if regulated by the first column, or if it's AW class, you're going to put in your prescriptive building, it's U.38. And so the delta between 0.38 and your actual 0.25 product that you're going to use being so much more gives so much benefit to your model that that's the reason for the increase in flexibility. Now, energy codes need components, and so extrapolating from that previous example, it could benefit from some good windows. So before we get into windows specifically, let's look at the term that I've been using, design flexibility. Let's look at targeting the weakest link. So flexibility and responsibility go hand in hand. If we're going to be able to do almost anything on the building, more and more, you need to be responsible collectively that those assemblies meet the desired result. So I'm going to suggest that if you start by getting the enclosure assemblies performing well, everything else involved in your energy modeling and the calculations get so much easier, and easier involves less cost and more options for products and more options for changes in design. So let's look at a hypothetical building envelope here. When I say get the building performing well, pretend we're designing a multifamily mid-rise building. And since we know that windows are typically the weakest energy link in a mid-rise building exterior, we're going to have more wall than window, approximately twice as much wall to window. And then I've learned from energy modelers in our industry that compliance with these two latest energy codes generally is easy and flexible if the enclosure as a whole has a performance of around R7 to R9 effective. So let's take the midpoint, R8, and we'll keep that target in mind, as we go through the design of this building. So let's go to a tool, and I'm going to go to the one that's on our company's website, cascadiawindows.com. It's an area weighted RValue calculator, and it's under the tools section of our website. The simplicity is that you're permitted to create inputs of the effective R values of multiple assemblies like windows, walls, and you can even add a roof. So I'm going to go to that right now, actually. Here is the R value calculator page, and if you scroll down, here it is, and you can add another assembly like I just mentioned, the roof. And then you can assign areas to these inputs, and then the output is the whole building's R value. So we said the walls, the area was 60%, the windows, the area was 30%, and the roof, the area, we'll give it a 10%, because we said we were going to have double the amount of wall to window. So the value to making these inputs and getting that output is that you can make changes in real time on any one of the inputs, and you can see the result of the R value change on the whole building. So for example, if we take a 15.6 R value for the wall, as per previous ASHRAE codes, if we do an R25 for the roof, and if we do an R2 or 2.1 for the windows, which is what you can commonly expect from a thermally broken aluminum window type, you can see that the results are out on the right-hand side there, and that the total R value of the building is 5.4. So remembering that we are targeting an R8 for the midpoint of this to get the envelope working effectively, and obviously we're not there. So we need to address the issue. We need to address the assemblies here and figure out how can we get this to R8. So let's start by improving the walls. So let's double the insulation thickness, and let's add some thermally broken cladding attachment, and we'll get the walls performing to R30. And you can see that we increased some, but we're still only at basically 6 for the effective R value of this whole building. So let's also improve the roof. Let's go from 25 to 45. A very well insulated roof. You can see we only jumped up about 0.07 R value. So maybe 450, even though that's not possible or plausible. You can see that the incremental improvement from improving the roof doesn't get us where we need to be. So let's go back to R25 and R15.6 for the walls. The point I'm trying to make here is that we need to address the weakest link, which in this group of assemblies is the windows. So if we go from an R2.1 to a double glazed high performance window product with an R4, which is what you can commonly expect, you can see right there we're all of a sudden above our building's R value target of 8. So now if we were to take that one step further and choose a triple glazed window with an R value of 7, which is what you can expect for some high performance triple glazed products, you can see that now we're way over. We're up into that 11, almost 12 effective R value range for the building envelope. And so what does that do? That allows us to maybe reduce the amount of exterior insulation on the wall. We can go down to, R11 or something like that to whatever thickness is required, or gives you the highest floor space ratio or whatever you're addressing in your design, and we're still above that 8. Or if we kept those walls performing well at 15.6, potentially we can change the proportions here. So varying the glazing area, we don't have to have double the amount of walls to window. In fact, we could flip this on its head and see what we need. So a triple glazed window with a well-performing wall and a well-performing roof will give us that total envelope R value of over 9 with 60% window and only 30% wall. So a mid-rise building that has 60% of its envelope being window appears to be almost all glass, which is, you know, a very appealing and very good for the occupants as far as light and what's desired from those types of buildings that we described earlier, like the offices and condominiums, etc. So that's an example of the flexibility in design that comes with using tools like this to get the enclosure performing well as a starting point, and then the rest of it becomes relatively easy. So go back to the presentation here. So specifically, what does this all translate into? Well, basically as much glass as you want on your building if you approach the codes like this. So 60 to 65% appears like an all glass facade, as I mentioned, on most buildings. Exterior insulation on concrete buildings, yes, and steel frame buildings, yes, you'll need some exterior insulation. With wood frame buildings, maybe not. Maybe a small upgrade to triple glazed windows can outperform the original design that included exterior insulation and allow you to remove it. So you can save money and cost and wall thickness, et cetera, with changes like that. Mechanical systems as well. All of a sudden, more economical and smaller sized systems will be sufficient to provide the energy required for the building, which does a few things. It obviously reduces the cost and the complexity around a system like that, but also increases the amount of tradespeople and qualified contractors that are available to design and install and work on systems like that. So they become less specialized. And so for larger commercial buildings with very intricate mechanical systems, sometimes those can exclude a large number of contractors. So your pool of qualified trades is very small versus reduced complexity in the mechanical system, thanks to a better envelope, gives you more efficiency, more people to choose from, potentially a bigger home, potentially a larger floor space ratio. And all of this with an improvement on the envelope components, specifically the weakest link, which is usually windows, and moving from double to triple glazing can have significant impacts on the flexibility of your design. Go on to the next slide here. So here is some example of the increased glazing area and what that looks like. This is a building that's modeling the amount of energy usage. This building is just within the acceptable range. So the thermal energy demand intensity is at 35, and then the thermal energy usage intensity is at 111. So if we change from aluminum window wall to a fiberglass window wall, so an improved thermally improved fenestration system here with fiberglass, you can see that the thermal energy demand intensity drops down to 30 and the thermal energy use intensity drops down to 106. So now we can do something like increase the percentage of glazed area window to wall ratio. So if we go to 45, that's what it looks like, and you can see we're still at 30 and 107, 50%, 30 and 107, 55, 30 and 107, 60%, 108, 65, 109, and you can see with 65% window to wall ratio, the facade has an appearance of being predominantly glass or almost all glass. What about a low-rise building? So this is again a building on the left with an aluminum window wall that's right at the limit for energy usage. And then you're looking on the right at a fiberglass window wall equivalent, so switching from aluminum to fiberglass. And all of a sudden you've got flexibility to increase the amount of glazing area up to 55% and significantly improve the look and the amount of glazed area on a building like that. Still complies with the energy code requirements for that building. So now we'll try and understand modern windows and give an introduction here into high performance fenestration. So high performance is usually frames made of polymers. Typically, there's 4 types, but not always. You're not always pigeonholed. There's wood frame. And this is an aluminum clad wood frame that you can see. There's vinyl and UPVC options. There's fiberglass frame options, and there's aluminum, thermally broken aluminum frame options. Typical applications for these frames, residential for the wood frame and aluminum clad wood frame, residential and multifamily, a lot of time wood frame multifamily for vinyl and UPVC windows. For fiberglass, residential, multifamily, and commercial high-rise. So you're seeing those frames used in all those building types. And then aluminum, more so multifamily and commercial high-rise. So for the purposes of today's talk, we're going to focus on commercial and high-rise buildings being traditionally thought of as too difficult or too complex or too expensive to incorporate high-performance products into. So we'll go through a little bit of the history of window performance. And in the 1970s, we had basically metal and glass, one layer that would give you an RValue of less than 1. And so then in the 1980s, 2 layers of glass were introduced and an insulative air layer between them, giving a over 50% performance improvement. But it also came with a cost premium of about the equivalent amount. So about 57% more for that window delivering an R1.1 than the previous technology that was delivering R0.7. And so you can see that there's about a 36% improvement when we went from the 1980s to the 1990s and introduced thermal breaks into the frame. But that also came at about a 30% cost premium to the previous example. And then in the 2000s, instead of air, argon was introduced as the filling material in between, and increased the performance by about 20%, but also increased cost by about 20%. And so in the 2010s, we saw low E coatings going on all glazed units and contributing to, again, another 20% approximately improvement in energy performance and also a 20% cost uptick. And then finally, regulation kicked in, and regulation dictates better products in this case. So now not only does the frame need to be thermally broken, but composite and higher performing frames can increase the performance by up to 172% at essentially a cost neutral equivalent. So you don't need to pay more for high performance anymore. It's being regulated, and manufacturers are coming to the table with these improved products for about the same cost as what we were seeing there from the 2010s. So traditional, commonly thermally broken aluminum frames are shown here on the left. And you can see that the frame is making a huge difference. The fiberglass frame just moving that heat loss out. And so that's really what's responsible for higher performance, is the frame. And if we look at a punched window, typical versus typical double glazing, you've got about an 85% improvement. So the example on the on the screen now is from Cascadia, and so these are our double glazed and triple glazed R values. You can expect an R4.1 from the double glazed and an R7.1, which represents an over 100% improvement and then 250% improvement in performance level there. So the big picture context is that 30 to 50% of buildings' heating and cooling energy is lost through its windows, and the frames are the building's weakest link. So the frame is where the technology, and it makes the building performance easier once you get the windows right and higher performing. So easier and more flexible for cost optimization. So now we'll talk finally about cost optimizing high performance fenestration options. So this is the definition of high performance. This is what you can get. This is available from many manufacturers, and this is the range that you should be expecting. R4 plus for double glaze, R7 plus for triple glaze, and then at the slab bypass areas for commercial buildings, the spandrels, you can see that there's R16.2 or R19 available depending on the installation thickness that's used, and that represents a massive improvement over previous options that have been available there. Cost savings when designing a window. So how do you get high performance with a modest cost? There are some tricks, and one of them is simplicity, just reducing the complexity previously maybe required for strength that isn't required anymore due to technology improvements. Simplifying that complexity reduces the cost, and then spreading the cost over a larger square footage. So larger windows are actually cheaper per square foot than smaller windows. So some key takeaways as we wrap up here. The BC Energy Step Code and Seattle Code update in 2018 involves a whole building approach, so a one energy use limit for that building. The passive elements of the building enclosure offer the most significant opportunity for compliance. So that's windows and doors and insulation versus active components like mechanical systems, etc. And by improving the weakest link, the weakest R value makes the biggest whole building gain. And we saw that when we used the calculator. So finally, again, a reminder of the Cascadia offerings. We've got the fiberglass punch windows and doors. We've got fiberglass strip windows, fiberglass storefront glazing, and fiberglass window wall, the commercial fiberglass option with the slab bypass shown there with insulation behind. And then finally, the thermally improved cladding attachment system, the Cascadia clip, used there with exterior insulation for those high-performing walls to be used with high-performing windows and that high-performing building envelope. So that concludes the presentation. I'm just going to come back on camera and thank everybody for their attendance today. Thank you very much for listening. Really appreciated your participation in the poll. And there were a couple of questions that came in. Is any of the details that I discussed available for download on the website? And I would like to go back to our website here, so just show everybody that yes, there are a number of documents and further information available at cascadiawindows.com. If you just scroll down to the bottom of our product pages, you'll find all of the downloads that are available. So someone was interested in details, and those are available in PDF and DWG format, I should say, for download, as well as some spec information and some installation information and videos, etc. So please go there. I encourage you to check that out. If you're interested in other webinars, those are also listed on our website. So you can go to the webinar section on the top of the banner, and I referenced some of the other webinars that are available. There's one on passive house that's been very popular. So I'd encourage you, if you need any last minute credits before the end of the year, or if you're just interested, please do sign up for other webinars that we offer, and we appreciate your participation, and hopefully we'll be able to work with you on a project in the future where you're looking to optimize the performance and cost optimize your building and your project. So please do reach out if you have that opportunity. Thanks again, everybody. Appreciate your time, and hope you have a great rest of the afternoon and great holiday season. Take care. Bye-bye.